Okay, welcome back, everyone. We are here in part one of the workshop that John Clippinger and our partners at First Principles First are coordinating. So, with that, for the next session, please, John, to you, and take it away.
Well, thank you very much. I would like to just to share a deck with the group here, if I could, and provide a sort of an overview of what we'll be talking about in this particular session. Can you see that now? Is this good for you? Okay, great. And we'll be anticipating with Andrew is Bashir will be coming on and providing the tutorial. But what I would like to do is, in the first instance of this, is being able to provide an overview of why active inference is important, why active inference agents, this whole perspective that we're taking here, is worth people's attention and paying and being concerned about. And what it has to offer to address some of the limitations of the current AI systems, for example, the large language models and some of the agentic architectures that have come out of them. And in that context, what I am looking at is sort of what is the current state of large language models and agentic and agents. And I think there's a lot of activity that's been talked about, but there is still no mission critical applications yet. There's a lot of exploration. You have people like Salesforce developing little Einsteins that can do various kinds of workflow automation. You have Copilot and Microsoft, but it's not really core critical. Not to say that it won't be, but it is still on the experimental phase. And it's still a black box. We do not know a lot how it works. Hence, you have issues of data provenance. You have a question of how to govern it. And there's a concern about you've invested $1 trillion, but there's an unknown business model coming out. So there's a lot of money that's going into it, but it's not clear that the current framing of AI, as it's now known, is going to be viable. And part of the issue here is that and I love this example from the New Yorker, is like who's modeling whom. We're actually putting data into the models. We're training representations and we have that interaction, but there's not necessarily an abstraction that's coming out. So it's kind of this relationship of seeing ourselves, mirroring ourselves, and going into this sort of cycle. And what we have now is a certain hype cycle. So it's around the peak of this is 2023 from the Gartner Group. And it's the generative AI is at the top of the hype cycle, and then it's hard to read this particular graph, but you'll see that principled AI is basically on the early cycle. It's on the early phase of it, but it's not seen as taking very long. Where something like you're going to have AGI is seen as being like 20 years out. It's the top of the hype cycle. I think if we update this. There's now, I think it's starting to be appreciated that the generative models and the expectations and the kind of problems and the costs associated with them, and then the lack of improvement, the lack of degree of improvement through successive models is starting to show through. So the next generation OpenAI shift strategies, the rate of GPT AI improvement slows. In other words, the new Orion model did not have the level of improvements that they were expecting. I think that is something to take into account. And hence the cost of training and inferencing is extremely high. And with that, the fact that you have this enormous consumption of energy, that Microsoft is going to have to recommission 3 Mile Island and drive one of their own data centers. This shows the impracticality of having to have so much computation in order to have work and make these models work. And I think that this is starting to be recognized within the limitations of large language models and sort of the parametric approach to modeling AI modeling. And I think just start to step into what we have now, what we're looking at. I mean, I love this is like another cartoon from the New Yorker, and it says to think it all began with letting autocomplete finishing our sentences. And well, autocomplete is a sort of form of Markov chain. So we are having this sort of chains on top of chains, and we've been able to develop some pretty rich representations of human activity text and actually forms of cognition, but there's not an underlying model there. And so what we're looking at, there may be some foundational issues that are coming up in very large language models, and that the fact that it is a black box, it's not explicable, it lacks internal causal models. There's not a way of reducing the complexity. It's sort of a batch processing. There's no real-time updating, and that batch processing we see is extremely expensive. And so we're caught on that issue. It's not agentic. It has no notion, no means of a spontaneous adaptation and correction on its own. And it suddenly doesn't know what it doesn't know. And it has no way of representing its completeness of its knowledge and adapting coherently to that. And also I would say it's not derived from really sort of fundamental scientific principles. It's really sort of an engineering phenomenon on a case-by-case basis. Now this is changing. And I think the same issue, if you start to see foundational issues for multi-agent LLMs, in other words, the transition to making agentic architectures where you can create a particular agent that's optimized to do a particular task or role. A lot of the success of that agent is depending on the quality of the prompts of that. And sometimes those prompts are good, sometimes the prompts are bad, but there's not a really principled way of doing that currently. And so they have a very fixed way of and specialized kind of goals. It's sort of a mechanical, it's sort of the instantiation of an industrial model that we see. Now, what we rather than having a sort of biological self-correcting model, it is sort of these fixed static models. Now, what I would say the active inference difference here is that it's really developed from first principles, and I think and I think you're going to see that Andrew's going to go into this much more detail. But it cuts across different disciplines that themselves have been maturing fairly quickly in the last 2 or 3 decades, and so it is going in basic physics, quantum information theory, the whole idea of computational science, biology, and cognitive science. All these are intersecting into creating a new way of looking at what intelligence and life are and how they're interconnected. And it also builds on well-established statistical methods, including Markov blankets, Bayesian belief models, the stuff that work has been done with JDA Pearl. And basically what you look at active inferencing does, and just to highlight, is it codifies a predictive brain thesis that's been nurturing in neuroscience. And so and then that in turn sort of mimics the processes of the scientific method. And so we think about what the method is that you're trying to codify, and I turn to Richard Feynman's comment, well-quoted comment that what I can't create, I can't understand. So there's a new kind of criteria for what it means to have to understand something, is be able to model it, to create a digital twin. If I can recreate something, then I understand what it is, and if I can replicate that behavior, and that's sort of the principles that you find in active inference from the very beginning is, how do I create a generative model? How does a living agent have a generative model of itself and its world? And this really owes its work, its origins back to the work that's done with J.D. Pearl on his understanding of causal reasoning and also Markov blankets. What is an autonomous thing? And this is where Carl Fritz and Donald's work. How does something maintain its separation from the world in which it is in? And so it is not governed by that things, but maintains its autonomy. And there's a certain kind of topology there that and something has certain kinds of internal states, it has external states, observer states, and action states. And there's a lot of deep concepts that's in it. I'm sure Andrew will go into that much more detail. And then what we have is the active inference agents themselves as sentient live things. So you're creating something, and this is very different than, say, a large language model. You're something that has agency, and it has a representation of itself in the context in which it's trying to stay alive. And so it's self-organizing, it's self-healing, it's self-replicating, and it's symbiotic in the sense that it evolves complexity, mutual synchrony with other living things in its world, in its niche. It's a joint niche construction. Hence, sentience is sort of a kind of situational intelligence, an awareness that's grounded in the survival of that particular agent. And the person that's sort of the context of the person who's really behind this is Carl Friston. And my own experience of being someone who was very interested in sort of in artificial intelligence from many years ago, and self-organizing systems of cybernetics, it really hasn't been until the last 5 or 6, maybe 10 years that this has come together in a coherent, not only a coherent theory, but a whole coherent formalism, and to what Carl would call a physics of living things. And he's one of the most cited scientists in the world as a neuroscientist that's done, basically developed a reputation in neuroimaging and inferring the structure from the brain from neuroimaging. And he applied the free energy principle, which we'll go into more discussion to later. And so I love this idea of a trefoil knot. It's sort of like, okay, it is sort of this autocatalytic biotic system. It's really important that it's a living system and it has certain kinds of characteristics that are all intertwined with itself. One cycle synchronizes its extraception, or it's a representation of the external world to minimize uncertainty. The other does it internally. It has to align that with the external world. And then you have another cycle that has expected free energy minimization. It makes predictions about how to change itself in its world. And so what we have here is basically what I think active inference offers is a soundness, a grounding in biology and physics. And so you have a sort of a ground truth of evidence base. Do I make predictions, and do those predictions allow me to act and survive in the world? So it can be explicit, it can be explainable, and we'll talk about this later, but you can have, since it has causal models and language and knowledge graphs, it can explain why it's doing what it's doing. And also it can explain how much it doesn't know, this degrees of uncertainty associated with it. And there's also the potential self-policing, self-correcting mechanism. And I think this is really important. In other words, you can design a active inference agent to live within certain constraints and bounds, and you can build in certain mechanisms that have for self-governance that cannot be captured. So its actions are within the limits of its design mission and not to generate negative externalities. So I will sort of leave with this one, and then just to quote William Blake, who talks about this in a poetic form as a fractal nature of reality. See the world in a grain of sand, and heaven in a wildflower, and hold infinity in the palm of your hand, and eternity in an hour. This just sort of pulls it together in a more poetic sense. So on this, I would hope to hand off to Andrew. If he's, thank you. Still.
Great. Yeah, thanks, John. And so, hi everyone. I'm Andrew. Andrew Pache. I'm currently involved with the Active Inference Institute. It's been great partnering with Dr. Clippinger, with the director of the institute. You know, we've been doing some really exciting work lately. And I want to address a lot of the points that John has made, although most of that will come tomorrow when we give some major updates on our biofirm. So today, in the spirit of like an initial workshop and kind of introduction to active inference, I'm actually going to refer back to this tutorial that I gave a couple months ago at an international conference for computational social science, meaning folks who are involved in sociology, economics, a broad range of fields. And the context was applying active inference, a lot of these principles that John is referring to social science research. And I basically make the claim and the argument, this is already being done, so I'm not necessarily providing a bunch of new information, but it's just to kind of extend the dialogue to computational social scientists, like, here's how we can apply active inference to, your particular setting in different ways. So we'll just kind of cover some of of what I went over. And, I apologize if there's any whiplash from how quickly I go through these slides. But we're just going to move a little quickly. So the context again of this tutorial that I gave was it was split into 3 parts. It was a 3.5-hour workshop where we started with talking about agent-based modeling, how it's traditionally been done, and then followed by that something that I would call a cognitive turn in agent-based modeling that's happened over the past couple decades. As there are these kind of calls for, we have the computational resources now. We have an immense amount more of, empirical research and validation of different kinds of principles related to human cognition coming from neuroscience, neurobiology, cognitive modeling, studies of neuronal dynamics, organisms in their environment, all those the kind of things. So there's a shift to that. And then the most recent, means of trying to establish that in the broader state of the art area is using reinforcement learning agents. So we'll touch on what those are and kind of how that works. And anyone who's kind of been looking at the agentic framework for what's being done today, they'll probably already be familiar with reinforcement learning. Then after that, we'll go into active inference and how that kind of bridges together a lot of these different things. And apologies, I want to just mention real quick. You can actually go to this link. The quickest way of following that is just by going to Google, type, my name, Andrew Pache, and then you could type GitHub or IC2S2. In any case, you'll come up to the landing page for this. You'll see links to all previous slides I've made, slides that I'm making for tomorrow. I'm also making a lot of this open access. So there's code that people can play around with and things like that. So agent-based modeling. This has been done. This goes back to roughly 70s, 80s with a lot of initial developments of computer technology and being able to realize that we can simulate people, right, in some loose sense, in some kind of simplistic sense. How can we simulate people? And why would we want to do that? We would want to do that so that we could maybe imagine hypothetical scenarios. Imagine you're designing some kind of policy or want to test a policy and see, if I recreate that in a simulation and have people in the environment where I'm implementing that policy, what happens? What's the collective outcome? What occurs? And so there are all kinds of fascinating work from Schelling and the traditional way of looking at housing segregation, for example, handling those kinds of problems. Where do people land? How do they settle? In like a residential environment. Even more interesting work later after that, Santa Fe Institute recreating an artificial stock market, where you have agents who are basically interacting with this kind of financial environment where they're looking at stock prices changing. They make choices to, buy or sell, etc., and see how that plays out. Recreation of housing booms and busts. Excuse me, not housing, financial. So this can be applied in many different ways. Point. And so what is agent-based modeling, in its fundamental principles, and how does that relate back to active inference, which we'll get to? Key components of agent-based modeling is that we have agents, kind of the catchword of the day. Traditionally, agents are, they just represent some entity, a living organism. This can be used for biological and zoological studies of trying to understand, how ants or insects interact in environment, or at a broader scale, how humans and entire societies and cultures might interact with their environment. And so what's really important about this with agents, environments, and simulations is that we just kind of run a simulation over a series of time steps. And so we let dynamics play out. And then what is it that composes those dynamics? It's the assumptions we make about agents. What is their behavior? What do we think that they do? How do we program them in this way or in that way? And then also, what are the aspects or characteristics of the environment? And so again, given that a lot of this work was done starting in the 80s going forward with very, we're nearly archaic at this point, forms of like computational resources, it's like things were kept as simple as possible. And there are a variety of guidelines that need to be used to develop agent-based models for running these kinds of simulations. And so some of them, even running up to 2007 here, this is the work of Doctors Laser and Friedman, who are respectively have been involved with Northeastern University and Stanford. They give some guidelines for how to do this. Guideline 1 and 2, in sum, is you need realistic assumptions that you're making about your agents, but not too realistic in the sense that they're too complex. One, because we don't have computers that are advanced enough to run highly sophisticated complex agents. And then also, if we make too many assumptions, then the situation won't generalize well. You might be making an agent-based model for one very, very particular scenario where it's not adaptable across different real-world circumstances, right? So we need some kind of balance in terms of the complexity of the assumptions we're making and the simplicity of the assumptions we're making. The rest are a bit more plain, which are one, reproducibility. You should publish your code. You should document it very well. Other researchers should be able to kind of take up the torch and be able to experiment with your code. We at the Active Inference Institute, we're constantly putting out new GitHub repositories and documenting our processes so that other people can come and get involved. So I just, want to mention that there's a big problem in reproducibility in science today, and it's very well known. So just want to touch on that. And the non-triviality, it's like, why do agent-based modeling if it doesn't help us uncover anything? Why not just sit down and have a conversation about, what do we expect to happen? What are our thoughts about what's going to happen? Why, do all of this with setting up these programs and agent-based models and designing them if we couldn't just come up to the same conclusion through speaking? So you want your results to be interesting, and you want to make realistic assumptions that, we can kind of have all these things synthesized together. So I made some points about balancing simplicity and complexity. This is just a representation of, these are common problems in machine learning and deep learning. You go and get, the university education. These are the core components of all of your courses. This isn't specific to active inference. This is like wide-ranging, concern. How do you create a model that is realistic enough to capture and explain the phenomena you're looking at, but simple enough to where it's adaptable to different circumstances. And there's, these are kind of in part, just as Dr. Clippinger referred to Richard Feynman. Just some reminders from famous statistician George E.P. Box. All models are wrong, but some models are useful, right? We're always trying to approximate a reality, and so the question is, how do we come closer to approximating our reality? And so how do we actually, using modern computational resources, using all of these new advances in all these fields, how do we actually make, new forms of what we'll call cognitive agents who exhibit the kind of mental dynamics and social dynamics between them that actually better approximate real human behavior? So I give some definitions, the differences between traditional agent-based models and what agent assumptions are being made. And more often than not, for the sake of simplicity, an agent is pretty one-dimensional. If they observe X, then they do Y. Otherwise, they do Z. These very simple pre-programmed rules. They're not autonomous. They're kind of like, you can think of them as like thermostats or something like that, right? If the temperature is too high, you turn it down. If it's too low, you turn it up. That kind of reactive framework. There's no beliefs about what's going on. There's no internal goals per se, aside from a single homeostat that is, maintain the temperature at what you set. Cognitive agents, however, the expectation for those, this is throughout the recent agent-based modeling literature, is like, how do we achieve cognitive agents who exhibit internal cognitive mechanisms? They exhibit perception, action. They actually learn and update their models. I'll make a point that, as John referenced, in the case of LLMs, which I'll cover much more deeply tomorrow, LLMs do not, it's so expensive to train them, and you typically just train them once, right? And so they don't learn in real time. they're kind of stuck with the knowledge that they have. They have a lot of it, to be fair. They've been trained on, thousands of documents, and so on. But that's it. Like, that's what you have, and then we have to figure out how to work with LLMs from there. With cognitive active inference agents, as well as other kinds of cognitive agents, the idea is that they can learn in real time, meaning in the moment, and adjust their expectations and their beliefs to what's actually going on now. And then also planning. So the capacity for being able to infer or guess using evidence that they take in, like what's going to happen in the future, right? And that's immensely important in today's climate, right? That's in part the reason we're doing agent-based modeling, is to attempt to plan, to test things, to come up with our own inference about what's going to happen in the future, and then act in actionable ways to realize our own goals in the future, right? So that's ideally that's what an agent would do and be capable of. And then with this cognitive turn, we're also looking at a broad synthesis of all these fields. As John mentioned, we're looking at things like cybernetics and machine learning. We're looking at physics, information theory. People are starting to. It's great. It's fascinating that so many interdisciplinary conversations can come up and collaborations between researchers of various backgrounds, because it's like, once we realize what it is we're trying to do here, we can start to pull from maybe principles or relate principles from other fields to this field. What works, what makes sense, what's empirically, what can be validated, and so on. So it's a very rich field right now. And then furthermore, a lot of traditional agent-based modeling has been done using software called NetLogo, which is very specific. It's good if you want to do agent-based modeling, like you just learn this one programming language. There's a GUI, like an interface for using it. It's highly simplistic. It is not integratable with other tools, not integratable with LLMs, with natural language, all those kinds of things. And it's very narrow. It's good at what it does. With cognitive agents, we would want to be able to pull from all kinds of other resources that are available, including open source ones. Being able to use APIs, being able to pull in other kinds of real world data, not just purely simulations. So there's just a lot of richness behind this idea of moving to cognitive agents. And then there's some basic, ideas of what makes a cognitive agent. Again, perception. They take in observations and they infer what's going on in the world. And kind of like what we do. My stomach growls and I infer that I'm hungry, for example. It's a very simplistic example. And then agents are generative in the sense that they actually come up with their own plans or choices of what actions to take based upon what they believe, such as I observe my stomach is growling, I infer I'm hungry, I will now choose to go eat food as like an affordance that's available to me in my environment. So this is a new way, in a certain sense, of doing agent-based modeling, where before we were looking at modeling an environment with a bunch of one-dimensional agents, predictable agents on the inside. If they see X, then they do Y, otherwise they do Z. But now we have models in a model, in the sense that we're actually able to internally inspect our agents, right? By having this beliefs-based framework where agents observe real data or information and then infer beliefs about it, we're able to then retroactively look inside the agent and see what its beliefs are, as opposed to these kind of, very difficult to interpret black box models that we find very commonly in deep learning and very, very highly performative, yet very difficult to interpret, like neural networks and architectures like that. With agents, we would want to be able to see in almost like a human sense, like what are their beliefs that they're holding and why are they doing what they're doing. So we need to be able to accomplish that in order to actually realize all the additional benefit of doing this, which is being able to look at internal cognition. What are agents learning whenever I implement a new policy or something, right? I want to be able to know what's going on with them internally. I want to know the full impact of what it is, this plan I'm considering like actualizing. So to bring it back, how do we address all these traditional criteria? How do we make realistic assumptions? How do we how do we make our code reproducible? That's an easy one, because it's like, well, we're still coding the whole time. And then how do we derive useful insights from this? And what are other problems that are going on? Like now that we're getting into cognitive architectures, um, and we are starting to brush up against the potential of recreating more black box models, right? We need to keep things simple enough. Like how do we navigate all of this? A common problem in social science research in general, but also in data science, machine learning, and those kinds of fields. Reinforcement learning, common issue is how do we handle what's called the explore exploit trade-off? This is famously an issue. If you have an agent who comes up with a suboptimal solution to a problem, let's say an agent who's they're trying to figure something out, they find something that they deem to be good, they get a positive reward signal or positive feedback from that, but it's suboptimal. There's actually a better solution exists. They just don't know about it yet. How do you get an agent to actually be willing to explore? And same thing for humans, right? We don't always stick with the first decent looking option available to us. Sometimes we explore in the sense that we seek better solutions to problems. And this is especially important and something to be addressed in agentic frameworks where if you're trying to use agents for, say, software application or a use case, like you want them to be able to find better solutions, ideally, at any given moment, especially in a changing context that might call going forward for better solutions. Say agents who are maintaining an environment that's subject to natural disaster or climate change, right? Like that might call for a whole new set of policies or actions that need to be taken, that couldn't be relied upon in the past. So we need agents who seek new information. Unfortunately, in reinforcement learning, that this is still an issue. People are trying to figure out how to kind of manually define what defines exploratory behavior, and it tends to boil down to kind of simple mathematics of defining, like, okay, well, we'll modify these agents so that 90% of the time they go with the best solution they know about, and then 10% of the time they'll just pick something random. That way they're at least exploring 10% of the time. You could put it that way. Active inference, again, I'm sorry, I'm kind of zooming through a lot of this. Recall this is an over 3-hour tutorial. But with active inference agents, this kind of gets naturally resolved in terms of what's called the free energy principle, which we'll be getting into. But basically, the idea is if you're able to have agents who naturally seek information, perhaps in line with how we do, right? That when they come up against something, they see, oh, there's value in seeking new information to find even better solutions than the ones I already have, and being able to do that in a way that isn't some kind of ad hoc rule of the 90% versus 10%, as I mentioned. That's kind of a key component, a key consideration in designing agents. So this brings us to the active inference, which I describe here as a framework for doing agent-based modeling. It begins with the free energy principle. I'll make a lot of mentions to this nice textbook that Thomas Parr, Carl Friston, and their other co-authors published a couple of years ago. But there perhaps even some more updates to be made because it's such a lively field. But that textbook really lays out a lot of the core principles and ways of getting started with active inference. The free energy principle: everything that changes in the brain must minimize free energy. Now, despite all of this interdisciplinary communication, dialogue between, again, cybernetics with psychology, with behavioral economics, that actually sounds quite simple, right? To be able to boil everything down to, oh, we have a brain, it's trying to minimize free energy. That almost sounds simple enough to where we might be able to employ that as a kind of simple assumption that we made in agent-based modeling. It's quantifiable. It's a presumed is the wrong word, but something like a principle that can be applied in any given circumstance whenever we're looking at these organisms who are self-organizing, such as humans, such as living organisms, such as plants in an environment that's being taken care of. that they exhibit this kind of characteristic of minimizing free energy as a form of quantifiable uncertainty. So we'll touch back on that again in a moment. But what active inference provides is a kind of normative, holistic framework for what I argue should be applied to agent-based modeling. It itself addresses agent-based modeling. That phrase is used in the textbook. This is not a foreign, out of left field kind of invasion of active inference into agent-based modeling they're proposing. There's so much overlap, and I think it's just an underutilized connection that's already been made, right? Active inference is based in it provides neural process theories, meaning that we're not just assuming in the same way with agent-based modeling we might assume, oh, all people are utility maximizers. In this case, we're not just assuming it. We're looking at neuronal dynamics. We're looking at decades of research into using neuroimaging studies and looking at how does the brain really function, how does it handle uncertainty, different kinds of behavioral studies and tasks where you can record fMRI or EEG along the way and look at the dynamics of those of that data that's being collected along the way, and then from there we can start to kind of model how that works. So as I already mentioned, we're still looking at a kind of belief-based framework, which is to say, we're looking at for agents who have beliefs and they update their beliefs, and they do that by way of the free energy principle, which is minimizing uncertainty. We start to see these organisms that we're modeling, humans or otherwise, they start to have naturally emergent adaptive behavior, right? By trying to figure out what's going on in your environment and then adapting your actions in order to better understand it, to better realize your own goals, you're effectively minimizing your uncertainty. And the free energy principle basically is a kind of free energy is like a proxy for that uncertainty that renders a lot of these things computationally tractable, meaning that we're able to quantify it, we're able to record it. Whenever we run agent-based modeling, we're able to actually look on a chart and a graph how much of free energy is being reduced over time, and look at the agent's internal beliefs about, what is it that they're figuring out within their environment over the course of the simulation. The view from this perspective is that another aspect, I already addressed the exploration-exploitation balance and trade-off, self-evidencing. This means that agents, in order to minimize their uncertainty, one way that they can do that is to try and act to realize their goals. There's something they want, something that they expect, right? And so it's as if you have this prior set of beliefs of what you want to see in reality. This is the this is the kind of framework that active inference deals with, but also referring back to Judea Pearl, as Clippinger mentioned. This is a kind of Bayesian idea. This is rooted in something like Bayesian statistics or even mechanics, where the idea is that you have your prior knowledge, you bring it to the situation, and then that will impact how you update your beliefs based on new information, right? So we're not always starting from some blank state, some starting from scratch. We're always coming to a situation with what we thought before, and then that gets updated. How does that get updated from active inference? That standpoint is through free energy principle. So I made some points in this tutorial because I realized we're really I want to make sure we have time to kind of bring this back. But with active inference, that we already have so many aspects of reinforcement learning and active inference which overlap. We're trying to create cognitive models. Active inference, I don't want to say it's necessarily competing. I don't know if that's the right word, but it's making advances that reinforcement learning is trying to make itself. And with active inference, it's like, well, with active inference, we're actually basing this on, a variety of principles, that, again, sorry, zooming through, we're able to cognitively model what's going on in the mind in various ways, that reinforcement learning is really lacking today. It's really lacking that. These models are being built to be highly performative, but they're missing the mark whenever it comes to something like realism and basing these reinforcement learnings in something like a science that extends beyond just the mathematics of machine learning. Right? We want to be able to find biological, physiological substrates for how all of these things happen, right? We want to be able, from there, to be able to apply everyday words and interpretability. So, what is it that defines what a habit is? What process is involved whenever a goal is formed and made, and then from there, attempted to be achieved through action? What defines planning? What is prediction? Um, and so I just want to see if there's anything else I might be able to touch on. This was a nice, for anyone, and maybe I should have started with this, but this is a little bit more of an intuitive glance. And these are not words from Carl Friston, surprisingly. They're from Sarah Feldman Barrett, who's at Northeastern. She's, nearly as reputable as Carl Friston in the neuroscience field. And I just personally, as someone who's also interested in neuroscience and cognition, I find her work fascinating. She's done a lot of work on emotions and kind of affective neuroscience. So it has to do a lot with looking at what's going on inside the mind of especially humans. And so this is kind of trying to provide an intuitive glance at how can we think about Bayesian frameworks, about inference, about active inference as well. So it's like this is a long quote from a podcast that she did. Your brain receives sense data from the world, sights and sounds, and smells, and so on. Receives sense data from the body. And so when there's a loud bang or a tug in your chest, your brain receives that information as the outcomes of some set of causes. But what caused that loud bang? What caused that tug in your chest? Your brain actually doesn't know. It only receives the outcomes. It has to guess at what the causes are. This is called an inverse problem. You know what the outcome is. You don't know what the cause is. So your brain has another source of information available to it, and that is past experience, memory. Apologies for just like doing a slideshow karaoke here, but you can read it for yourself, I suppose. But the point is, and with some of this highlighting, it's like we're actually taking account of a variety of things. We're taking account of interoception, meaning observations that arise from within the body, or for an active inference agent, it has to kind of model itself. I mentioned earlier that if I'm hungry, this goes beyond the five senses in that kind of perspective, right? Touch, taste, feel, all of that. With this, it's like, well, I need to understand what's going on within my body. I need to understand what's going on outside of my body, as Clippinger, referred to earlier, the idea of a Markov blanket. It's kind of like I need to figure out what defines the boundaries between myself and what's around me. On the one hand, I need to have a model of myself in order to maintain it. Otherwise, I succumb to the environment around me, to use some of the language that's used in the textbook. It sounds a little bleak, but we're referring to real world circumstances. If I don't take care of myself, I will naturally decay. Like that is kind of the sort of the principle. The world is entropy, so to speak, right? It's like if I don't eat food, I fall apart. So I need to have a model of myself, what's going on within. I need to have a sense of what's going on without. And then I need to be able to kind of synchronize those things in such a way that I can continue to exist as an entity within this environment around me. And that's a very intuitive, perhaps not very well technically described, but for now an intuitive sense of kind of what defines a Markov blanket. So this is a sort of foreshadowing for tomorrow. We'll talk about this really interesting project we're working on called the Biofirm. With Daniel and under guidance of John, in that sense, we're trying to develop homeostatic agents. Homeostatic meaning agents who, their own sense of their survival is predicated on the homeostasis of their environment around them. So we're trying to create agents who actually take care of and attend to the environment around them, as if their own survival depended upon it. This is a very interesting kind of flip. Where where you actually want to match and model the environment around you, but also take care of it in a way that you can maintain it within those bounds, just as I have to eat in order to maintain my energy levels. The agents need to take care of their environment, within some kind of range to where it has, enough caloric energy, so to speak. Um, so I think for now, John, is there anything that you think I have not addressed that might be useful to our audience, or if anyone else would like me to touch on anything, maybe something I skipped or otherwise, I'd be happy to speak more.
No, I think you've covered some of the really key points that what I think is what we've done is what differentiates active inference from the more traditional agent-based modeling. I think it's important because when people think about agent-based modeling, they sort of default to what the traditional models are, and I think that you've done an excellent job of sort of highlighting what the difference is and what the having that broader perspective and that more grounded interdisciplinary perspective, you're able to more not only represent the complexity of it, but also provide a way of modeling agents within that complexity. And I think that the notion of the homeostatic nature of an agent trying to live in conjunction or really harmony with the world around itself is depending upon its survival and its ability to stay alive and differentiate and have complexity, but the synchrony of the environment is really another key point. Because I think, well, a lot of people, they think, oh, well, you may say, like navigating a fitness landscape, you're just trying to optimize different levels, but in fact, the landscape itself is shaped. You're doing joint niche construction, so it's a much more complex notion than traditionally understood in general modeling. And I think in consideration of what we're looking at tomorrow, this whole idea of the mimetic character of modeling, having it based upon principles in biology and nature, and being able to create an economic agent that acts that way, I think is really quite important. And so maybe some people have some questions about that we want to focus on or not, but that's something that I think it's important to highlight.
Yeah, awesome presentation, Andrew. Ernesto, if you have a question, also anyone in the live chat is welcome to ask a question.
No questions. Thank you very much. This is so inspiring.
But Ernesto, just to put it in context, I know this is something that you're very interested in this whole idea of a bimetic economic system, and you've been looking at this yourself. So this is really trying to lay down the principles, really the scientific principles and computational principles of doing this, and we'll get in more to that tomorrow. But that's the intent here.
Yeah, a lot more to say. Again, in our remaining 40 minutes, I'm happy to read questions from the live chat. I'm also happy to screen share and look at some of the registered participants' backgrounds and interests.
Sure.
Okay. Okay, you can unshare, Andrew, and I'll pull up some word clouds. All right. Okay. Okay, so let's let it load. Okay, these are word clouds that are generated from the participants' registration information, and we'll zoom in on them, and I'll just kind of mention them, and we'll zoom in, and if anyone has a remark or something that they want to like highlight or call out about it, just go for it. Okay, so this is a word cloud of the 150 or 200 registered presenters overall, asking about what is your personal background. So the biggest, and this is scaled just by number of uses of each term. So one person mentioning a term a ton of times might make it large. So just to be taken as sort of a representative, we see those tiny two letters, AI, which could mean almost anything at this point, and a lot of other terms like computational research systems, neuroscience, cognitive, philosophy, social, academic, robotics, technology, practice. This kind of speaks to the broad range of topics that leads people into joining in it, at least entering that information on the form. Any thoughts on this, or we'll keep on exploring these word clouds?
Okay.
Okay. All right. Again, just raise your hand or go for it.
Interesting.
Okay.
Well, I'm interested in the notion of community and systems. I mean, applications. The community seems very strong.
Yeah. Yeah, and that's the center of a later one. So
Yeah.
here we asked what would be useful, and by asking what would be useful and what would be interesting, we alluded a little bit to the dual composition of the expected free energy. What would be useful, what would be utility, what would be pragmatic, and then what would be interesting, what would be epistemic. So here in what would be useful, here we are in applied active inference symposium, wondering about how does active inference go from being a unifying framework for ecosystems of shared intelligences and all these different kinds of things that we've heard already and we're going to hear in the symposium to come. So interesting that systems, a way to operationalize and really move forward from framings of complex adaptive systems to having the implementations and also the community and the people understanding research, models, collaborators, and then a lot of different topics that are being explored in more mainstream computational science fields like multi-agent algorithms. Andrew alluded to that and kind of brought that up in the context of the Goldilocks parameterization question. The agent-based model can be so simple, it gives you a great intuition. It shows at a demonstration layer how simple behavior can lead to complex outputs. On the other hand, the agent-based modeling can go the other extreme where it's so sophisticated, then it loses its transferability. So that's what people would find useful. And then here's what they put for what they would find interesting.
Mm-hmm.
Applications make sense, as that's what this symposium is all about. And again, a lot of other ideas thinking about different specific systems, research ideas, architectures, synergies, toolkits, insights, implementations, support, collective directions. Here's asking, what would help you in your learning and applying active inference? And community looms large, other people, as well as some of the more tool, resource, textbook, education, examples, frameworks, interactive tutorials, different languages, Python. What does anyone think about this?
I'm a little surprised that we're not seeing the phrase LLM anywhere. I just kind of noticed that. So one of the points that I have been trying to work out and I hope to speak more on tomorrow is um, you know, integrating active inference with LLMs, and there have been attempts to do this, and even with Kristen and Parr and other folks, there's been attempts at trying to pull out an agent's beliefs and then use an LLM to process those beliefs, like kind of decode them and re-encode them in natural language, so to speak. It's as if the agent is speaking and saying what it thinks and believes, and why it did what it did is, another layer of interpretability. And I don't know, I'm slightly surprised to not see LLMs anymore. Maybe it's a little too, maybe that's a little too on the frontier right now. I know it is in many other areas, and it's, sorry, in the couple minutes we have, it just, something that I've been working on personally, and this is feeding into the bio firm, is how do we use LLMs in a way that we can actually integrate them with all these major priorities that we have, where we want to have agents who actually have defined goals, right, and ways of trying to stay alive, in a way that they interact with their environment in a way that it's as if their own survival depends upon it. We don't want LLMs, which, again, I'm just saying this quickly, I don't mean to sound disparaging, but LLMs in one sense can act as like functionally as talking heads, where you just send in some text and they try to predict what would be the best text in response. They're still subject to hallucination, to confabulate, making things up, so to speak, even though the answer looks structurally sound. And so my point is that rather than viewing LLMs as agents, I don't think they are. I think that you could have an active inference agent who is augmented with the capacity for natural language by having it interact with an LLM. Right. So
Yeah.
sorry to
Yeah,
go so
I mean,
deep into
this is
precursor of my own talk, but yeah.
scanning across all the registration fields for LLM mentions. So, how does active inference apply to the design of LLM systems? AI outside of LLMs, better ways of designing internet scale protocols and governance systems, and should converge with tiny ML to challenge LLM's deep learning. So it is interesting that it's referenced with only a glancing blow, and we've even seen earlier, like in the responses to similarities and differences with reinforcement learning with Friston earlier, about the increased amount of
Right.
attention and tool development and the later and more professional maturity of training environments. And this is like one of the key foci for the open source active inference ecosystem and for the Institute, is to develop those kinds of methods and trainings and all onboardings, all these different aspects of increasing the professionalization. So let's look at the challenges. So this was, what are the challenges facing your learning and applying active inference? People, interesting. The problem and the solution. Models, the math, software, maths again, mathematical understanding, difficult physics, scaling, simple examples.
It's interesting, because in the larger conversation about what AI is, I mean, it's that conversation is so dominated by large language models and quote generative models within large language models. And well, at least I've been observing, and I tried to refer to my initial slides, is that they're starting to appreciate the limitations of the large language models, move towards more agentic models and more towards causal models, and hence creating agentic architectures that do work with large language models, but they're still they're still not based upon biological principles that we're discussing in active inference. There's sort of more of the mechanical models being applied over it. And I think to me, from a point of view of sort of the sociology of science, or there seem to be these different worlds that I mean, the number of people that I've known sort of in the open AI world, they're very unaware of active inference, and some of the critiques that are, if you listen to the Gary Marcus, he's got a very pointed critique of of large language models and not being able to achieve abstractions, but that doesn't extend to appreciating what the opportunities are in active inference. And so there's sort of these islands of understanding that they still exist. And I think that's one of the challenges. And when you talk about developing an infrastructure, I mean, there's huge financial resources that are going into the large language models infrastructure. And where I think the totally biased on this, I think all the opportunity is totally within the active inverse of free energy principle, and I think that's where the science is going, and yet it's sort of in this isolate world. And I think the only way to get out of that is to really start to show the applications and showing with results because but it's interesting. I mean, to say that they're different worlds. But I think that there's a peaking, and so the hype curve around the large language models, and they're going to descend. My bet is they're going to descend into a valley of doubt, and you're going to see that showing up in the Nvidia stock going down, and then people are saying you can't destroy all the natural resources or run these models. You don't have to, the other thing, and Carl alluded to this in his earlier comments today. I mean, he was talking about climate change and models and compression, and I think that's going to be a driver of this. But that's some my observations on these clouds is, yeah.
Oh, I'll bring in a question from the live chat. Also, welcome, Mao. Just thought I'd bring you on if you wanted to participate in this panel or just chill. So, Stephen Sillett wrote, is the lack of LLMs mentioned because large language models are different to dynamic agent belief modeling?
And do you want to take that? I mean,
yeah. Could you repeat that? Question.
Is the lack of LLMs in the word clouds here, but just more generally thinking about similarities and differences between active inference generative models and LLMs, is that because large language models are different than dynamic agent or belief modeling?
I don't want to approach this question in the wrong way, but I will say that as far as whenever it comes to LLMs and dealing with their internal parameters are obviously highly quantitative, and then they're dealing with natural languages tokens, and then switch back to looking at active inference agents, which are highly quantitative in nature. And typically, if you're making continuous time models, you're looking at, again, quantitative information. And then even with discrete models, you're looking at, these kind of discrete values that you could potentially move in the direction of trying to, make it. I think this has already been done, but there are agents who have been used to try and understand, like, we can read individual tokens, then move up to another layer, and then we have entire sentences, and then move up to another layer, we have entire paragraphs or ideas. That kind of thing is done. But I think this kind of like LLM with quantitative grounded agents, like that connection is still, in my view, that's kind of the frontier of where things are at. And so it's difficult for people to conceive, like, how can we translate, encode, decode, re-encode natural language in a way that's readable by these quantitatively oriented agents? And then vice versa, how do we transition quantitative beliefs into natural language? That's the very thing that I've been looking at, thinking about recently. I made like a active inference, like PLMDP agent who, what they do is that they use their beliefs about which action to take, and then that action that they carry out is actually corresponding to a prompt to an LLM. And then you can actually take those beliefs, the quantitative beliefs, find some way of meaningfully interpreting them, and then putting that into these blank spaces in the prompt as if you can have the agent say in real time, I currently believe this with probability this, give me, a solution to this problem, based on that. So being able to find this kind of numeric versus the quantitative and the qualitative, it's a historical problem when working with data that goes back centuries at this point. So it's really exciting though. It's really exciting to think of how to bridge that kind of gap, and I still haven't seen anyone, nail that down. This is the frontier. This is where we're at, and I think that's kind of the next thing for everyone to really be considering, thinking about, working on. And I'll give my view on how that could be done tomorrow. So.
Mel?
Yeah, I mean, effectively, LLMs don't really encode explicit beliefs or really maintain a persistent model of the world. Even when we sort of give them a sort of loop by which we communicate with them, that loop in itself doesn't actually factor into the predictions that it's going to do. So they just lack a framework for recursively updating beliefs, which is probably why it's not being thought of here. But also mainly that, LLM agents are only agents by virtue of sometimes being connected to stuff and having explicitly stated goal, but I don't think that actually qualifies them to be agents.
I totally concur with that. From my perspective, I think that the reason that LLMs are not looking at are not looking at, or that whole mindset is not looking at belief structures in intersubjective experiences, I think is a product of a whole sort of objectivist, reductionist methodology that has been tuned not to look at agentic systems. I mean, in my generation, if you were in biology, you were in and you talked about agentic systems, you were outed. I mean, that was verboten, and I think there's a whole school of thought. There's a whole set of in a Kuhnian sense, a normal science built around a sort of objectivist, reductionist, non-agentic notion, and so it's a new generation that's coming in both in biology and in modeling and cognition. There's recognizing this notion of an agentic perspective of beliefs and updates, and that's a huge shift, I think, in sort of the epistemological perspective of a lot of what has been traditional science.
That's really interesting.
Cool.
There's also just operationally the difference between taking a very large fixed number of parameters in a given model, 70 or 7 or 405, training on existing data, and then finding patterns or eigenmodes or activation summaries that have secondary interpretability. But there's not really an effort of trying to find interpretability at the level of activation of a given neuron. It's about looking at patterns and trying to find collective level interpretabilities, like in the AI interpretability field. Contrast that with designing from the ground up an example agents where the beliefs are explicitly encoded numerically. And so that's a different mode of building, and also one that's hinted at in this 2023 paper with Mao and others, that highlights that element of explicit semantic interpretability and also explicit semantic interpretability of uncertainty estimates. Whereas a string of tokens emitted by an LLM that says, I'm not sure, it's sure about saying that, but that doesn't mean that it has a given certainty about the referent. So understanding what the communication semantics of LLMs are is incredible in what they do. And I think when we look at this cloud for people's responses, how can active inference make a difference in 2025 where there is LLMs? Here, many kinds of systems, and that's sort of like a microcosm of what the symposium is, different people with different systems of interest asking how do these different attributes of the model that we're talking about, the first principles, grounding, semantic interpretability, surprise and uncertainty, and its bounding as a central component as opposed to reward, how do all those things really play out? What does that demonstration look like in different systems?
Yeah.
Here's another.
Really like,
go for it, Andrew.
No, I was just going to say on that previous one you were just looking at, I really appreciate that kind of broad-mindedness that people seem to be exercising. I like seeing terms like symbology, scientist, governance, industry. I mean, those are some I'm very excited to see people who want to, so much work has been put into kind of the theoretical and then sort of like in vitro and in lab and in simulation kind of work that's been put into active inference. So I'm just really excited to see, with the international the conference, the active inference conference that was given recently, and being able to see like a drone that's flying based upon the free energy principle and things like that. I'm just really excited to see more like kind of real world applications, right? And kind of creating systems and applications for like real world use cases. It's really cool to see some of those terms there.
Yeah, I think that's going to be really critical. See, yeah.
Here's the cloud for how are you applying active inference. Again, systems, I think just reflecting people talking about variety of different systems types, and also reminding me of my own journey to active inference, being excited about complex adaptive systems, however, not really having a software toolkit or a formal way to proceed past, okay, we think about nested multi-agent systems, and then where's the software toolkit? And then we're right back to where Andrew showed us on the slide. It's like, well, we can do a really simple one in NetLogo, or we can engage on this enterprise scale engineering research program. And here's a more incremental, interoperable way to have portfolios of motifs and generative model components and be assembling and scanning across these different kinds of compositions, like 3 ant nest mates in the desert, 3 nest mates in the forest, and these different kinds of environments, being able to compose them. And over the last several years, seeing a lot of the advances in the category theory, in the first principles physics surrounding all of these sort of research things. And it's like, that's kind of the water drawing out. And then that's the question about how it looks when it is applied. And that's what I guess we convene around in this symposium and are seeing differently in 2024 than in previous years.
Just curious. So, what's the change that you've seen in previous years versus this year, and then so looking forward, more of an application?
Andrew or Mao, what do you think?
Yeah.
but absolutely that is, yeah, Matt,
Yeah.
please.
Yeah, I mean, I feel like the work of Maxwell Ramstead, Casper Hasp, I mean, obviously Carl, but a lot of people who perhaps came from more dynamics decided to take a real interest in what we could do with something that was so scale free. And I find that it's been really, really rich in terms of the different kinds of theories we've tried to sort of reformalize. I know that's most of my work is a reformalization of existing social sciences. And to your point, Daniel, the problem we still have is that we're missing like these key little plugs that, yes, you could couch as, just different schemes of message passing, but you still need some interesting tools to have a very good description of the vast variety of types of structures that we have, which social sciences have done a really great job at, if not intuiting, at least describing properly, but we still don't have the best tools to make accurate predictions. And that's part of the reason why most of our polls, when we make them, are nil, they're useless. And that should be the main thing we apply them to, is just literally just understanding where we're at, not even making predictions, just understanding where we're at. And we still fail at that. So I'm very encouraged by seeing this, and I hope that we will start valuing more and more interdisciplinary perspectives that are sometimes more technical, but also sometimes more philosophical or social.
Awesome.
Yep.
Also, while we're in this, in the coming workshops, tomorrow will be more of a bioregional, biofirm focus, and then day 3 will be entirely with Clippinger et al. On this topic, and I wanted to show one really operational open science crossover with LLMs and active inference, which is, and I'll put it in the live chat as well. Here, I used Perplexity, which does an internet search, summarizes and translates information using LLMs. So here, we'll pick on Alexi. There's a profile, a learning plan, and a set of small, medium, and large project proposals about active inference. So this is just summarizing expertise and experience. Here we have a learning plan. It's just a starting position, but this brings a new low bar to the kinds of resources that everyone can take on in their learning and use as like a syllabus or a curriculum, and even as an interactive tutor. It will not get bored with you asking to explain concepts again and again, or using different metaphors, or making it applicable, making it like this poetry format, putting it in this narrative context. And so even asking, how do I start with this, or can you help me understand what I don't know, that puts such a centrality and highlights metacognition in learning. And then the project proposals, each of them structured according to essentially what a grant officer would be looking for, and what a project manager would be thinking about in terms of small, medium, and large projects. So this unprecedented high throughput way to fuse even scanty input from a participant in a inclusive open science setting into real projects that, if enough people think, hey, that looks kind of interesting, then we're well down the road of actually making it happen using different kinds of funding, which is something Michael Lennon mentioned a little bit earlier. So it's sort of like we can get really detailed and technical and architectural thinking and finessing the differences between reinforcement learning, deep learning, active inference. And we saw slides to that, like when Carl showed the action perception loop, similarities and differences. And okay, active inference doesn't have a reward function. It's not optimizing based upon this trained auxiliary reward concept. It's just doing something direct with likelihoods. Like, that is critical. That is what makes the active inference generative models what they are. But then looking at something like this, which wasn't so accessible 1 to several years ago, that just feels like opening up and unleashing what people can do, and about using these as tools in our niche. And I think it's a total open and unknown what happens when you can get to this level of project and learning plan for an arbitrarily complex field with the patience of an AI that's just going to accept questions all day long. Like, that's almost the bigger applications question. Again, just zooming out from how the architectures and the parameters are similar and different to how are we going to do what is authentic and right and best given the tools we have. There's a bigger picture beyond just holding the magnifying glass to different computational artifacts.
That's well said, Daniel. I really agree. It's transformative.
If anyone has questions in the chat or here, or any other things they want to mention,
Yeah.
what's going to happen in the next 2 sessions, John, or what would be your goals or preferences for this arc of the symposium for you?
Yeah. So I think as Andrew alluded, the session tomorrow is going to be really on the application of active inference agents to a design of a economic agent, a new kind of firm, called biofirm, that's homeostatic. And the objective of that is to develop a new kind of incentive structures, a form of collective action that are based upon mimetic principles that I think we'll see address a lot of the issues that people are having in the whole idea of bioregional finance and how to deal with climate change and how to create those incentives. So one of the things I'll kick off with, I've been talking to a number of people in the whole fields of regenerative finance, what they call biofi. This it ties into the work that was done in Eleanor Ostrom's work on how common pool resource, how do you manage a common pool resource, how do you incentivize people at different scales. I really think that, and what you identify some of the requirements that people are looking for in order to address these problems at scale. And I think what we'll be talking about is to the implementation of active inference principles into an economic agent, that it provides, I think, a reasonable way of addressing these issues. And so that's part of the conversation that we want to have and bring together these two worlds. Then the third session is to really look at this from a broader point of view, is saying, where is this going? And so the people that we have in the panels are very much involved with enterprises, applying it to nonprofits, applying it to some problems, looking at what they can do with LLMs currently and what the certain current agentic architectures are, and what happens when you go to full autonomy. What does it mean to have autonomy in a biological sense, something keeping alive, and what does it mean to build systems that have autonomy? I mean, this issue of autonomy is sort of fundamental when people think of autonomous cars or decentralized autonomous organizations, or the whole idea of the central bank. The principles behind something like a Bitcoin is like, oh, that is autonomous, but is it really autonomous? And what is this new notion of autonomy if we base it on biological principles? And I think that opens the door to a very different set of discussions than we're currently having. And it also opens the door to new notions of governance and how we can build governance in to maintain the homeostatic states. And Andrew's alluding to that. So I mean that's where I become an optimist. And I'm not an optimist around the extension of LLMs and OpenAI and the tech the tech giants, but I am an optimist in being able to apply these principles to some of the fundamental issues we're having around climate and social equity and economic equity.
Awesome. Okay. In the closing minutes, if anyone has last comments, and David's question too, if you want to address it, Andrew or anyone else. Any thoughts about how we start to develop a multi-scale approach to ethics?
Hmm.
Well,
I want to allow time for other people, so I'll briefly say. So tomorrow, we'll present various aspects of the biofirm. There will be a little bit of a redux of some of the things I went through today, just to kind of thread the narrative, and I'll kind of talk about Homo economicus and all these kinds of assumptions about human behavior and things like that. But multi-scale governance. What we're trying to do with our biofirm is to, and Clippinger referred to Eleanor Ostrom's work on the commons, and so I'm going to address that a little bit too. But the idea is to be able to have a kind of like adaptable system of multiple agents, and so we have a kind of small society, so to speak, and they're kind of governing the commons around them. And by being able to have something like the capacity for one, shared goals, and two, adaptive learning, such that they can actually adapt what they do and what they believe and the actions they carry out, have those be localized to the current context, which is an essential part of Ostrom's work. Is it's not so simple to just give a singular top-down instruction that applies in all places. I mean, to be able to have that kind of adaptivity and awareness of the local, while at the same time having agents who are kind of synced up in these various ways. I think that's one way of trying to approach governance. And then from there, you might be able to have kind of layered, you could have individual hubs, and then you could have some kind of interconnecting system between them that extends that to an even broader scale of multiple hubs and interaction between them. So just some breadcrumbs there. Right. Thanks.
Yeah. Mao, and then John with the last word on this session.
Yeah, so I mean, the question of ethics is it's obviously complicated, but the key part about whether we coordinate around multi-scale goal sharing, etc., shared potentials, that's intrinsic to hierarchical active inference, right? It just is. The question that isn't going to be solved is what is good, because you can always say, well, what is good by virtue of being contextually sort of stable, but there may be other ways to be stable or that might prioritize other kinds of individuals or entities, etc. So I don't think we're going to solve that question. However, what we can solve is the global versus local coherence of certain kinds of beliefs relative to what might constitute goodness at given scales, and find where the friction points might arise, because this version of goodness is incompatible with this version of goodness, and therefore something's got to give somewhere, an error is going to have to propagate. So I think that's going to be answered, but the larger, broader question, you'd have to look into different schools of thought around what constitutes good, because we don't necessarily want to go towards moral realism, because there's a lot of things that are baked into that. But you might want to go into the ethical implications of neo-materialism and how it is about interactions and locality. And at that point, it becomes about how do certain pockets of ethical frameworks sort of form and allow to just coexist away from other pockets, and what happens when they start interacting, which again, we may be seeing right now in the US.
Yes, good point.
John, any last comments on the session?
No, this is great. And I think we're now surfacing some of the issues that are really important to talk about. And I think at least what we're going to be presenting is a framework that at least we can have these discussions in a more rigorous way and a testable way. And I think that's part of the way moving it forward. So, yeah.
Awesome.
Thank you.
Okay, we'll take a 1 minute break. See you soon.
Okay. Thank you.